Earlier today, I put up the first homework assignment. Remember, so you're not going to be turning those in, but I promise things are going to go a lot more smoothly if you do them when they're assigned, get them done by the next class time, or, you're not turning them in. So if something happens here and there and you can't get it done right at the right time, right by the next class, that's fine, but just try to stay roughly on schedule and things will go a lot more smoothly, okay? I have a lot of office hours, and so if any of these problems give you trouble, feel free to come in, or even if they haven't given you trouble yet, just come to my office hours and sit there and work on it, and if something comes up, I can give you a hint or whatever. So, but I would definitely recommend getting started now, Okay, so we ended last time with that math quiz that's designed to give you sort of an idea of what level of math you're going to see in this class. I just wanted to go through the answers of those, solutions for those. Okay, so the first one was plot the function y equals x squared. That is a function that's going to come up all the time in physics. That relationship is one that we'll see a bunch of times. And so there's sort of two ways to do that. The first one is just to happen to remember the shape of that graph. That's the sort of easy way if you happen to remember. But if you don't remember, just choose a few x values and plug it into that function and calculate what the associated y value is until you start to see enough points that you can estimate what the shape looks like. You get a parabola, so something like that. The second one is to calculate the slope of the line that goes through the 2 points, 1, 2, that's one set of coordinates, and the coordinates 4, 3. So I'm going to plot these 2 points out so you can see kind of what we're talking about. 1, 2, 3, 4, 1, 2, 3, 4. Okay, so the first set of coordinates is 1 along the x-axis and 2 along the y-axis, so there. And the second point is 4 along the x-axis and 3 above the along the y-axis, so there. And if you connect those 2 points with a line, it looks like that. And we're trying to figure out what the slope of that line is. If you remember that the slope is the rise over the run, you can think of that as from the starting point to the ending point. And by the way, it doesn't matter whether you call this the starting point or this one, as long as you're consistent for the rise and the run. So first we want to figure out how much higher we go. That's the rise. So from here to here, how far up does it go? 1. And then for the run, we want to figure out how far we go horizontally. What's that distance? 3. So the slope is 1/3. What would that line look like if we got a slope of 0? Horizontal, yep, just totally horizontal. And so if you have a positive slope, it means that it's from a horizontal line, your line is rotated counterclockwise. And if we had gotten a negative slope, that would mean that it was tipped below the horizontal line, like rotated clockwise from the horizontal line. If anyone has any questions as I go through, please feel free to stop me. The third one, we just want to simplify the expression A times B squared times C squared divided by B to the fourth times A times square root of C. And I think the easiest way to do this problem is to remember that there are exponent rules for division and multiplication. So let me go through those. So first, for multiplication, if you have some number or some variable to the, let's say, the m power, multiplied by that same variable, and that's important, where these x's have to be the same, to the n power, you can just write that as x to the power of m plus n. And then for division, if you have x to the m power divided by that same x to the n power, the answer to that is just x to the power of m minus n. So whichever one is in the denominator, that's the one you subtract. Okay, so I'm going to use that here. So I'm going to write this as a to the, so in the numerator, we have a to the first power. In the denominator, we have a to the first power. Well, you can think of those as just canceling, but I guess I'll write it with these exponent rules. So we have a to the first power divided by a to the first power, so 1 minus 1. And what's anything to an exponent of 0? 1. Yep, so that's just not going to appear in this factor. Then we have b multiplied by b. In the numerator, we have the power of 2. In the denominator, we have the power of 4. And then for c, in the numerator, we have the power of 2. In the denominator, what's the power? 1/2. Yep, so this is to the power of 2 minus 5. And so you can write this as b to the minus 2 times c to the 1.5. And b to the minus 2, you could also write that as c to the 1.5 over b squared. So to do this problem, you just kind of need to remember how exponents work when you're multiplying and dividing. Number 4, we had an equation and we wanted to solve for a. The equation said a squared times b times c is equal to 4c plus b squared times c squared. Well, if we're solving for a, we want to get that by itself. So I'm going to divide both sides by bc. We get a squared is equal to 4c plus b squared c squared all over b times c. And then, so now we have a squared by itself, but we want a by itself, so take the square root of both sides, and you get a is equal to the square root of all this, 4c plus b squared c squared over bc. And then it's almost done. Well, you could still fiddle it, get a little bit different format in here, but this is the main thing that I wanted you to see. But there's one more thing. So this isn't quite right yet. When we went from, so this step is right. But what am I missing here? Plus or minus, that's right. And the way to make sense out of that is, so in any equation where you take the square root of both sides, you need to consider the possibility that your answer is positive or negative. Like think for example that what if a is equal to 2? Okay. If a is equal to 2, then you square it and all this is equal to 4, right? But now what if a was equal to negative 2? You square it, you still get the same thing. So we can't differentiate between a being, so say that all this stuff is equal to 2, or that I guess all this stuff is equal to 4. We can't differentiate between whether this is 2 or negative 2. And we're going to see in physics, I remember when I first did that in a math class, not really understanding not really understanding what the point was. But I think one of the nice things about doing this kind of math in physics is we're going to actually see, when we do problems that have this kind of stuff, we're going to see there's physical meanings associated with both of those two answers, Like, for example, this will come up in the projectile motion of an object. And the positive answer means something physically about what the ball's doing, and the negative answer means something physically. And we're going to actually be able to see the difference between those two, Okay, and then number 5, the last one. This was the one where you had to solve a system of equations. So the two equations, the first one was x1 plus x2 is equal to 50. And the second one was 2x1 minus 3x2 is equal to negative 10. There are a few ways you can think about this, and each of those ways is the fastest way sometimes and a slower way sometimes. I think unless you're really set on thinking about it beyond this, when I see system of equations, I would recommend that you just always think substitution. So I'm going to use this first equation, number them, or A and B. I'm going to use equation A to represent x1 in terms of x2, and then I'm going to substitute that into equation B, and then we'll have one equation that we can solve. So equation A, if I rearrange this to express x1 in terms of x2, we get x1 is equal to negative x2 plus 50. And now I can take this and replace the x1 with it. So equation B now says 2 times the quantity negative x2 plus 50 minus 3x2 is equal to negative 10. You have to multiply the 2 times everything inside those parentheses. So we have negative 2x2 plus 100 minus 3x2 is equal to negative 10. And now get all the x terms on the left, get all the constants on the right. You have negative 5x2 is equal to negative 110. Then divide both sides by negative 5, and finally you get x2 is equal to 22. So are we done now with that problem? Almost. We did the hard part, but we still have to find x1. So we have a whole bunch of equations now, right? We have the 2 we started with, and then 1, 2, 3, 4, 5, 6 equations. One of those can we use to find x1? We can use any of them, you know, as long as we didn't make any math mistakes. Everything here is true, you know. So take this, plug it in wherever it's easiest to calculate x1. I guess this one it's already solved for. So now take x1 is equal to negative 22 plus 50. And so x1 is equal to 28. Any questions about any of those? All right. Well, the first topic then and like I said about that test, if that stuff seemed, if most of that stuff seemed way beyond what you're used to in math, then we should talk about this class. Okay. So the first topic for this class is units and unit conversion. And the idea of units is, so first of all, every physics measurement needs to be associated with units. Like, for example, if someone asks, can I, like, how close is your phone? And you say 6 or whatever, that doesn't tell anyone anything. If it's 6 inches, then it's really convenient. If it's 6 miles, it's not very convenient. They'll just find someone else's phone, you know. So those units are an important part of that calculation. All the units that we're going to use in physics, well, in this class at least, there are a couple more types that we're not going to use, but all units in this class will be combinations of 3 basic types. Units of length, so examples of that are inches, feet, meters, miles, so on. Units of time. So examples of that are seconds, minutes, hours, and units of mass. And examples of that are grams, kilograms, the imperial unit slugs. It's harder for me to think of good examples for mass. And the ones that are going to be most important for us for doing calculations are meters, seconds, and kilograms. Any units made of those three, so made up of meters, seconds, and kilograms, are called SI units, Standard International. And those are the ones we're going to use by far the most in this class. But one thing that's going to happen a lot is we're going to be given measurements, Oh, yes. What? This probably not. Maybe late in the semester, possibly, but not for a while at least. A lot of times we're going to do physics calculations based on measurements that someone gives to us. We're not going to take all the measurements ourselves. And if someone else gives measurements to us, we can't control what units they're using. And so it's going to be pretty common that we're going to want to convert from, say, one unit of length measurement to a different unit of length measurement. If we want to use meters and someone gives us a length in miles, we need to know how to go between those two. So often, we'll want to convert a measurement from one unit to another of the same type. Okay, so for example, in simple cases, I mean, a lot of you have taken chemistry and you've done all the unit conversion you need, but for the rest of you, I guess, even in your everyday life, you're somewhat used to this unit conversion idea. An example would be, how many inches are there in 3.5 feet? So what I want to do is, that's sort of a simple case, and that's one that you could probably figure out just without really a formal method. But I want to come up with a method that's going to work in these simple cases, but it's also going to work in complicated cases when our units start to be things like kilogram, meters per second squared. There's units everywhere. That one isn't so obvious how to convert from that to the same, another unit of the same type. So here's the approach that we're going to take. Okay, so there's between two types of two units of the same type, there's always going to be a conversion factor that you're going to have access to. So two units of the same type always have a conversion. So in the example I gave above, we know that 12 inches is equal to 1 foot. And that produces two, what I'm going to call conversion factors. Both of those are just 1 divided by the other one. So the two are 12 inches over 1 foot. And 1 foot over 12 inches. And notice, since 1 foot and 12 inches are really the same thing physically, we can think of both of those as, you're dividing one thing by itself. You can think of them as both equal to 1. In other words, you can multiply anything by either one of these without changing the overall value of what you're multiplying it to. And so now what we're going to do is we're going to take our original quantity and multiply it by one of these conversion factors. So multiply our original quantity, that's an abbreviation, by a conversion factor. Okay, so in our example, we started out with this quantity 3.5 feet. And I'm going to multiply that by 12 inches over 1 foot. And you can think of those units as just algebraic variables. They obey all the same arithmetic rules. So the feet here cancel the feet here. The only units you have left are inches. And the number that's left is what you get from multiplying 3.5 times 12 divided by 1. And so you get 42 inches, and that's the answer. There's one thing you have to be careful of, though, and that's that only works because I just happened to choose the right one of these two conversion factors. Look what would happen if I chose the other conversion factor. So we have 3.5 feet. What if I had multiplied by 1 foot over 12 inches? Now the feet don't cancel, and if we multiply that out, we get the number 0.2916 repeating, and the units are feet times feet over inches, or feet squared over inches. Okay, well, it turns out, there's nothing wrong about this equation. Is not incorrect. 3.5 feet is equal to this many feet squared over inches, and that is a unit of length that you could use. It just isn't the one that we wanted. Okay. So we need a strategy for always choosing the right conversion factor for the units that we want. And so the rule we're going to use is, notice, you want to always multiply by the conversion factor that cancels the unwanted units. Okay, so if you go back to, original quantity was 3.5 feet. The unwanted units, the ones we're trying to get rid of, are feet. And so you want the conversion factor. If you're trying to cancel feet that are in the numerator, you need to choose the one of these that has feet in the denominator so those cancel out. Okay? That's why this is the one that we want. And this one doesn't work because if you use the conversion factor that has feet in the numerator, these just multiply, they don't cancel. I'll do a bunch of examples. I want to show you a shorthand that I'm going to use. So when I say 3.5 feet multiplied by 12 inches over 1 foot, I'm going to write that like this. I'm just going to give one fraction bar for the whole thing. Anything that's in the numerator of the fraction goes on top. And the ends of the parentheses, I'm going to give just with a vertical line. Okay, just save a few pen strokes. Any questions yet? Okay. So here's another example. Let's say we want to express 61 miles per hour. And by the way, that's 61 miles divided by hours in meters per second. So these are measurements of speed or velocity. Meters per second is the SI unit for speed or velocity. So we're going to start out with that original quantity. I'm going to put the fraction bar like that. I'm going to start out with 61 with the miles on top and the hours on the bottom. And we need some conversion factors. I'm going to write it here so people who read this later think I didn't forget it. So given that 1 mile is equal to, anybody run track in high school? What is this about? 1,600 about. Not exactly. So if you ran the mile in high school, you were actually a little over 9 meters short. It's 1609.344 meters. And then 1 hour is equal to 3,600 seconds. There was a guy, it's a long time ago now, but let's see, I'd say 2008 maybe, a high school runner at Burnsville who ran he has the Minnesota state record. He ran the 1,600 meter in 3:59. He would have been the 4th American high school student in history to run a 4-minute mile, except when you add the amount of time that it would take at that speed to run the extra 9 meters, it comes out to like 4.8 or something. And so okay, so we'll start out with 61 miles per hour. And then we can do it all in the same line. We're going to multiply by one conversion factor that takes us from miles to meters. And then we'll do another one that takes us from hours to seconds. All right, so we're going to go from miles to meters. We're going to either multiply by 1 mile over 1,600 meters, or we're going to multiply by 1,600 meters over 1 mile. Which one do we want? We want the miles of our conversion factor to be in the denominator to cancel out the miles in the numerator from our starting thing. So we have 1,609.344 meters over 1 mile. And then notice that if we just left it like this, I'm going to cancel these miles with these miles. Now we have our length units or meters like we want. It's just the hours we haven't adjusted yet. So we would, if we multiply these numbers out, we have the answer in meters per hour. Now we want to convert the hours to seconds. So we're going to either multiply by 1 hour over 3,600 seconds or 3,600 seconds over 1 hour. Which one of those do we want? We want the hours in the numerator this time because we needed to cancel the hours that start out in the denominator. So we have 1 hour over 3,600 seconds. And now those cancel. And the units we have left are meters divided by seconds, just like we want. And the answer to that is 27.26 meters per second. Any questions about that? Right. Okay, that's a good point. So let's do that. What if I didn't give you what if you only knew that 1 hour is 60 minutes? This is what you're talking about, right? Yeah. And 1 minute is 60 seconds. Well, you could just do it. It would just add one more step to this process. You'd have 61 miles per hour. You'd convert the miles the same way we did before, so 1609.344 meters is 1 mile. Then you know that 1 hour is 60 minutes. Yep. No, I'm not. I'm sort of going to ignore significant figures. I'm going to leave that to the chemistry teachers. They love talking about that stuff. So you can sort of round as much as you want. If you do the steps right and then round at the end to that, I guess that's all right with me. Okay, so what I've done now is, so I converted from miles to meters, and I converted from hours to minutes, but now we still need one more step that converts from minutes to seconds. We know that 1 minute is equal to 60 seconds, and so the minutes cancel. And so we have one more step in this conversion compared to this one. But if you multiply all those numbers out, you get the same answer. Yep. Yeah, I'll give you every conversion. Okay, and then there's one more type that you need to be ready for. So I'm going to do an example where I convert 38,640 yards per minute squared to meters per second squared. Express it in meters per second squared. And we're going to use the fact that 1 yard is equal to 3 feet. One meter is equal to 3.281 feet. And they'll always be given, yeah. And I mean, on the homework, they might not always be. You just have to Google it, I guess, if it's not given. You know, look up a conversion, like how many, you can look up how many feet in a meter or something. I know there on the assignment there is like a section that gives you a bunch of conversions at the end, but there might be a couple you have to look up. I can't remember. But on tests, I'll always give everything. And then 1 minute is 60 seconds. Okay. Well, it's given in yards. If I would have given you a conversion straight from yards to meters, then that would have been fine. But I didn't give you that, so we're going to have to do it in 2 steps. Okay, so our starting value is 38,640 yards. And then it's per minute squared. And so the way I'm going to do this is I'm going to write this as minutes times minutes. And first I'm going to, so the flow of what I'm going to do is I'm going to go from yards to feet, then feet to meters, and then minutes to seconds. So to go from yards to feet, to cancel the yards in the numerator of our starting value, we want the yards in the denominator of the conversion factor. And now we want to go from feet to meters. So 3.281 feet is equal to 1 meter. And if you cancel these things out, you see yards goes away, feet goes away. And our units of length are meters, like we want. So now we have to deal with the minutes. 1 minute is equal to 60 seconds. The minutes in the starting value are in the denominator, so I want to put them in the numerator of the conversion. So we have 1 minute is equal to 60 seconds. And if I do this cancellation, we can see that I'm not all the way converted yet, because here we have minutes times minutes. We've only canceled one of those. So we're going to have to do this one more time again to cancel the other minute. So again, the one we want to cancel is in the denominator. So we want to put one in the numerator. Is that for me? Oh, okay. Oh. Okay, so the last cancellation, minutes. And now we have length units of meters, time units of seconds. And if you multiply and divide out all these numbers, you get 9.81 meters per second squared. Anyway, that's a number that's a value that's gonna come up all the time. Anyone happen to know what 9.81 meters per second squared is? Yeah, so if something's in free fall, that's the acceleration that gravity is causing, if the air resistance is negligible. Okay, so let's do another one, and I want you to see if you can sort of think through this one. Okay, so let's say that we have a big block, a big cube, where the length of every side is 1 meter. And we want to know how many little 1 centimeter cubes would fit inside this box. So, like, you know what I mean? So this big box that's a meter in every dimension off the table is this high. And we're talking about little cubes this big. How many of those would we have to put inside to fill the big one? Centimeters, yeah. So 1, and we're going to use the fact that 1 meter is 100 centimeters. At first glance, it's not real obvious that this is a conversion problem, but it really is. The volume of this big box is 1 cubic meter, and the volume of these little ones are cubic centimeters. So we want to take we want a starting value of 1 cubic meter, and we want to convert to cubic centimeters. Okay. So see if you can work through that. Just take a couple minutes, talk to the people next to you if you get confused on something. And then I'll go through it at the end. But see if you can convert 1 cubic meter to cubic centimeters. I can't think of a way to do it without starting with the volume. I think you just need to start with that volume. Okay, if you can think of another way to do it and it gets the same answer, it probably works. But I can talk to you about it after. Okay, so our starting value is 1 cubic meter. And I'm going to think about that as 1 meter times meter times meter. And there's 100 centimeters in a meter. So I'm going to do 1 meter is equal to 100 centimeters. And if you cancel, you see that only one of those meters has gone away. So we're going to have to do that same thing 2 more times. So 100 centimeters over 1 meter. And then one more time, 100 centimeters over 1 meter. Those cancel. Those cancel. And so now we've gotten units of centimeters cubed. We have 3 centimeters there multiplied together. And the number is 100 times 100 times 100, which is 1,000,000. So it takes 1,000,000 of those little centimeter cubes to fill a cubic meter box. Any questions about that? There's 2 more things I need to talk about. The first one is scientific notation. And the idea of scientific notation is that any number can be expressed as one non-zero digit followed by a decimal point, followed by decimal, times 10 to some integer. So for example, the number negative 3,481.9 you can write that as negative 3.4819 times 10 to the third. 10 to the third is 1,000, so you get 1,000 times this, and that's the original number. And it works with numbers smaller than 1 too, like 0.0087 is equal to 8.7 times 10 to the negative third. So 10 to the negative third is 1/1000th. Multiply that times 8.7 and you get this. I was going to say something, but okay, so that's the idea. And by the way, this is doesn't really involve us because I'm not going to care about significant figures, but scientific notation takes away some of the pain of like, you remember when you had to learn the rules for how many significant figures a number has, and it's like, what do you do with zeros? Well, if the zeros are all at the end of the number and before the decimal, they don't count as significant figures. If they're after the decimal, if they're after the decimal, they're always significant figures. And there's these rules, and they're a little cumbersome to use. If you have a number written in scientific notation, it's just simply every digit before the times 10 to the whatever is significant, and that's the end of it. It's really easy. So for example, this one, how many significant figures does that have? If you look at this number, you have to remember the rules for where the zeros lie and whatever. If you look at this, it's just the 2 digits before the times 10 to the minus third. Okay, so there's 2 methods we have to learn. We have to do 2 things. We need 2 skills, I guess. First one is we need to be able to take a number that we're given in standard notation and express it in scientific notation. And as I go through, it's just going to be 2 steps. But as I go through these 2 steps, I'm going to use the example negative 541.6. Okay, so we'll say that that's the number that we're given that we want to put into scientific notation. Okay, so the first step is count the number of places, and we're going to count that number of places n, and you have to move the decimal point left or right to get one non-zero leading digit. So one non-zero digit before the decimal point. Okay, so in the example I'm using, how many places you have to move the decimal point so that there's only 1 digit before the decimal? 2, and do we have to move it to the left or the right? So we have to move it 2 to the left. And then if you moved it to the left, you're going to multiply by times 10 to the positive n. If you had to move it to the right, you're going to multiply by 10 to the negative n. In our case, we had to move it to the left, so we're going to have negative 5.416 times 10 to the positive 2. Any questions about that? Okay, so that's going from standard to scientific. We also need to be able to go from scientific to standard. So the second thing we need to be able to do is get a number in scientific notation and express it in standard notation. And for this one, the example I'm going to use is 6.52 times 10 to the negative fourth. So the first thing you have to do is read the absolute value of the exponent and its sign. The exponent is negative 4, so in our example, so the absolute value of the exponent, that's what I'm going to call capital N again. So N in this case is equal to 4, and the sign is negative. And now if it's negative, let me do positive first. So I did last time. So, sorry, if it's positive, move the decimal point n places to the right. If it's negative, move the decimal point n places to the left. Okay, so our starting value was 6. I'm going to leave the decimal point out right now. I'm just going to write the 652. But we started out with the decimal point between the 6 and the 5. Our n value is 4, so we're going to move the decimal point 4 places one way or the other. The exponent was negative, so we're going to move it to the left. So I'm going to start where it was and go 1, 2, 3, 4. Each one of those placeholders is filled by a 0. And so there's the number in standard notation. And you don't have to use that method. That's just a way for each of those that works. If you have a way that you're happy with, keep doing that. I don't care if you use that method, but if you don't have a way that you're comfortable with, here's one. Any questions about that? Yes. Yeah, on the work you show. I mean, to some extent, the answer, I suppose, but there'll definitely. So actually, that's a really important point. Is if like, don't just give me the answers. That doesn't do me any good. I want to see how you came to the answers, and I frequently give full credit on problems that have the wrong answer because people did everything right and just messed up some simple arithmetic or something, you know. No, I don't. With the scientific notation stuff, I don't think that really applies as well. It'll apply more when we get into like real physics calculations. But in the unit conversion, I do want to see the fractions written out. Okay. Any other questions? All right. The last thing I want to talk about is unit prefixes. And I'm just going to give you the ones that are really common. But, you know, the SI unit for length is meter, but you've heard of kilometers and millimeters and centimeters. All of those things, centi, milli, kilo, those are all these prefixes. The ones that are going to be common for us are micro, that's represented with the Greek letter mu. And you can think of each one of these as just meaning multiplied by a factor. So micro means multiplied by 10 to the minus 6. Milli is represented with a lowercase m. That's times 10 to the minus third. Centi is a lowercase c. That's times 10 to the minus 2. Kilo is lowercase k, and that's times 10 to the third. And then the last one we'll use a lot is mega. That's a capital M, and that's times 10 to the 6. And so if you're going from, if you're converting like, how many meters are there in 0.35, no, how many meters are there in 35 centimeters? You can just start with that value, 35, replace the prefix with the number it's associated with. So 35 times 10 to the minus 2 meters. And that's the end of it. You know, multiply that out. This is sort of somewhere in between scientific notation and standard notation. So really you should get it in standard or scientific, but this is equal to 0.35. Your calculator will do that for you. 0.35 meters. Yep. Yeah, I'll try to make that clear. That is a little bit of a pain, and that's something that comes up from time to time because there's only so many letters in the alphabet, you know. Yeah, so I guess if that ever comes up on a test and you're not sure which one I'm talking about, just come ask me. Okay. Any other questions about that? Yep. I took it to meters. Yeah. And so what if you had to go the other way? What if you had to go from like centimeters? Well, we started in centimeters and went to meters. So we started with a prefix and went to one without a prefix. What if you have to start in one without a prefix and go to one with a prefix? That's a little bit different. So let's say how many microns, micrometers, are there in 0.65 meters? So this time we're starting without a prefix and we're trying to add one. So the way, yes. Oh, okay. So the way to do that is to remember that 1 micron is equal to 1 times 10 to the minus 6 meters. And then just do it as a unit conversion. So we'll start with 0.65 meters. Our unit conversion has 1 times 10 to the minus 6 meters in the denominator and 1 micron in the numerator. The meters cancel. Dividing by 10 to the minus 6 is the same as multiplying by 10 to the 6. So you get an answer of 0.65 times 10 to the positive 6 microns. And that is 6.5 times 10 to the 5th microns in scientific notation. Any questions about that? Okay. There's no school on Monday, so don't come here. The building will be locked. And because I have labs on Monday, to keep all the labs together, there's no labs for the whole week, next week. So I'll see you in class on Tuesday, but there's no labs next week.